by 2070 and to meet 50% of its electricity requirements from renewable energy sources by 2030 is a hugely significant movement for the global fight against climate change. The scale of transformation in India is stunning. Its economic growth has been among the highest in the world over the past 2 decades, lifting up millions of people out of poverty. India's energy transition needs to benefit its citizens, and well-designed policies can limit the potential trade-offs between affordability, security, and sustainability. Professor Rangan, Banerjee, Speaker of the Day, Professor N.P. Badi, Director MNIT, my faculty colleagues, staff, and dear students, a warm welcome to you all to this lecture on India's transition and net zero future, a perspective. This journey of the Institute lecture series began with the inaugural lecture, which was delivered by Professor Ashutosh Sharma, former Secretary DST. The second lecture was given by Professor Terole, Nobel laureate. The third lecture was given by Professor S.S. Murthy, and the fourth lecture was delivered by Professor K.K. Chaturvedi. We are here today for the fifth lecture of the series on India's transition and net zero future, a perspective. And we are privileged to have Professor. To start with, I would like to request Professor Badi, Director MNIT Jaipur, to please welcome our devotee of Ma Saraswati. Then why not use Ma Saraswati? For the same, I would request Professor Rangan Banerjee and Director Sir to please come on the stage and listen the lab. I would now request Professor Badi to please address the audience.
Considering the restriction of time, let me not take longer duration, but it's my duty to welcome Professor Rangan Banerjee to this fifth Institute lecture series. We are privileged and honored, sir, to have you here today at MNIT campus. And I quickly welcome Professor Banerjee to take the dais over. Thank you.
Thank you. Formally introduce Professor Rangan Banerjee to you. In fact, I feel honored to introduce him to you. Professor Rangan Banerjee is currently the Director IIT Delhi. Before joining IIT Delhi, he served IIT Bombay as the Forbes Marshall Chair Professor in the Department of Energy Science and Engineering, a department that he helped start in 2007. His areas of interest include energy management, modeling of energy systems, energy planning and policy, hydrogen energy and fuel cells. Professor Banerjee serves on the editorial board of various reputed international journals. He has been involved in setting up a megawatt scale solar thermal power testing simulation research facility sponsored by the Ministry of New and Renewable Energy. He is the faculty advisor for Team Shunya, India's first student team in solar decathlon Europe, China and US panels. He has been involved in advising the City, State Regulatory Commission and Energy Agency, Niti Aayog, Planning Commission, MNRE on energy issues. Professor Banerjee is an adjunct professor honorary in the Department of Engineering and Public Policy, Carnegie Mellon University, and is a fellow of the Indian National Academy of Engineering. Now let us invite Professor Rangan Banerjee to deliver his lecture and enlighten us on today's topic on India's transition and net zero future in perspective.
So, good afternoon, and it's really a privilege to be delivering the 5th year back, little more than a year back. I didn't know that joining IIT Delhi as a director automatically makes you associate with MNIT, and we happen to be on the board of governors. MNIT is an institution where I've had good relationship in terms of, I visited only once. I'm not sure, I don't know how many of you, in 2018 I came for a PhD defense and I also gave a talk. Anyone was there for the talk? Okay, so some of what I say will be a repetition for you, but most of it is not. But anyway, things are sort of changed. But in that, when I was in the BO, I've attended a few of your BOD meetings all online, and the chairperson as well as the director have been keeping on saying that you must visit MNIT and talk to. So I told Professor Padi that I would like to come, and then he said then give a talk, and so that's how it is. So I'm going to, I would like to spend we have, I guess, about 45-50 minutes. I have a number of slides, but I'll skip some of them. I'll try and keep my talk for about 30-35 minutes so that we can have more time on the interaction. And I am going to give you a perspective on the energy transition and on net zero. And so we'll start off by, So as an energy system, when we think in terms of an energy system, and many of you have studied the system, you must understand that we do not have a demand for energy per se. Right? So for instance, today in this room, you are seeing these slides, and when you see this slide, what you are interested in is the illumination and the contrast. For getting that illumination, you have a projector which is out there, and then there is a bulb. Now, depending on the projector, if you see the bulb may have a rating of 200 watt or something. If someone tells you, I have this now, I will do some solid state lighting and give you the same illumination over there, and I will replace this with 20 watt or 30 watt. As far as we are concerned, we are indifferent to it. So we do not have a demand for the kilowatt hour. We have a demand for the energy service, for the heating, for the cooling, for the comfort condition, for the cooking. And so basically, the end use activity, the distance traveled, illumination, food, etc., the energy service. But in order to give us that energy service, we have energy which is available in nature, which may be coal, oil, natural gas. By the way, I'll make sure that these slides are shared with you. So, coal, oil, natural gas, available in nature, solar, wind, all available in nature, that is called primary energy. But that cannot directly give you the use or the energy service that we need. It goes through a sequence of conversion steps. And as all of you have known, you studied thermodynamics, when you do a conversion, theoretically, ideally, we can have a reversible conversion and everything. But actually, when you do this, you have finite. We talked about net zero. We are looking at, for instance, MNIT. You are getting electricity from the grid, from the distribution company. That electricity gets distributed within the campus, goes to your and then useful. So whenever we are thinking in terms of an energy system, we can look at the useful energy or the energy services, or we can look at the primary energy. And we can, of course, make each of these steps, reduce the steps, make them more efficient so that we use less primary energy. So that's one of the things that we can do. Also, if you see the history of human development, which we talk about, has been with an increasing use of energy. And if you look at, this is from the Global Energy Assessment, if you look at anything related with humans, right? If you look at anything related with humans, you see that the rate of the population in the earth, population in the world, is an exponentially growing, because dP by dt is proportional to P, number of people who are there. So if you take dP by dt proportional to P, you have an exponentially growing. Of course, it can go and it can saturate. Some countries have done population control and other things. But based on that, because of that dynamics, if you look at anything related with this, you see population exponentially growing. The output of the economies measured in terms of GDP, again exponentially growing. Foreign direct investment. We use rivers for our growth, so damming of rivers, water use, fertilizer component, consumption, paper, including McDonald's restaurants. All of this is exponentially growing. When you do it exponentially growing, just integrate and see with time area under the curve. Sun-bound. Sun-bound. What's the assumption? Infinite resources. Right? Not true. You have finite resources, one word. So this is a problem. So the question is, what is sustainable? Are our energy systems sustainable in the future? And this could be a topic of another talk, but we're not going to go into details of this. But I would suggest that you have, and this is something I would have talked in the earlier lecture also when I spoke about it. Look at this paper. It's a paper in Nature by Johan Rostrom et al. Those of you who don't like reading papers, you can see the TED talk by Johan Rostrom. Okay. He talks about a safe operating space for humanity. There's a whole group of researchers. What they did was, they looked at all the parameters affecting the globe, okay, and identified. So when you have a process under control, you can identify what are the key parameters which ensures that your system is having a safe operating space. So the idea was, how do we affect the parameters which gives you the safe operating space for humanity? And for each of this, with a historic growth, with the pre-industrial, nature has certain balances. So the pre-industrial levels were considered, the existing levels were considered, and then there were, for each one, a limit was identified, and then we will go into details of it, but I'd just like to tell you that one of them is the climate change, and I'll explain to you. The other one is biodiversity loss, the nitrogen cycle, many of them. You can see this paper, we don't have time to go into details. So for climate change, one simple thing, again this is something, climate change is now in, you've read lots and lots about it. Quickly just recapping everything, right? If you look at the earth and the temperature of the earth over a long period of time, thousands of years, this axis starts from 0 and goes back to 100,000. Okay? And what is shown here is an isotope of oxygen, the concentration. It is a proxy for the average temperature of the earth. When you look at this, you will find that there have been lots of fluctuations, ice ages, heating, cooling over a period of time. But in the last 3,000 to 5,000 years, we have had relatively stable temperatures. This is called by the geologists as the Holocene. And this is the reason why life as we know it today on the earth exists, because of this stable temperature. This, unfortunately, is now threatened by the very fact of its thing, by a term which is called the Anthropocene. What is the Anthropocene? Global changes caused by human activity. Global changes caused by human activity. Again, evidence of that I will show you. So, essentially, the climate change problem, first time we talked about it was in the 1950s. In the 1970s, we started having the IPCC. But nature has provided us a record. Now, if you look at the atmosphere, which are the most common gases in the atmosphere? Nitrogen, oxygen. Carbon dioxide is actually a much smaller in percentage. However, carbon dioxide is an important gas because of its capability for radiative forcing. You have these greenhouses, and in the greenhouses the incoming radiation comes in and then it gets trapped and it goes out. Temperatures are higher, you have a better sort of growth. Similarly, CO2 has a radiative forcing component, and because of that, the concentration of CO2 in the atmosphere, as far as we know, the only planet on which there is life is the Earth. And that is because we have this thin atmosphere which maintains the average temperature on the Earth to be 15.5 degrees. Right? So we look at, if you just Google ice core data, you get many data sets of Arctic and Antarctic. Okay? Typically what happens is you have people going on an expedition, they will take out the ice core, and in the ice core, as you go in depth, you can find out the date, the year in which it was formed. At that time, the air which was trapped when the ice core was formed gives you a frozen record of the composition of the atmosphere at that time. So nature has provided us this data, and this is typically this has the same pattern. Now if you look at this, you will see the first 800 years or so, it's like a process under control. 280 parts per million, absolutely natural equilibrium. I've drawn a vertical line here to show you that this, after this, the curve has a different nature. What happens here? What happens here? It's the
Start increasing.
yes, but why?
Industrial revolution.
Industrial revolution. Absolutely. James Watt and the steam engine start using coal to mine materials to make products, and now this represents the exponential growth that we saw, which is related to this, right? Clearly unbounded and goes beyond it. So this is the nature of, if you go to www.ipcc.ch, you get much more evidence, but basically link up the radiative forcing with this evidence, and you have the cycle of how global warming is happening. That is linked. This is data which you can get, and you will see that essentially we have now gone beyond 400 parts per million, and obviously this has implications in terms of climate change. We need to now look at limiting the total CO2 emission. The CO2 that is emitted stays over a period of time. It is emitted, whether it is emitted in New York or in Latur or in Jaipur, the effect is the same. It's a global problem. And of course, globally some countries have developed, they have used a lot of fossil, they have used their emission, and then the developing countries we want to develop, so there is a global problem. And so now we come back, so that was the overall problem. Now climate change is important for us for safe planetary, for the safe operation of the planet. We need to make sure that we are going back to that balance. And in order to do that, let us now look at India. Let us come back to now India. We are about 1/6 of the world's population, but we are, of course, not as rich as the average person in the world. We are 7% of the world's GDP and 6 to 7% of the world's primary energy use. So naturally our electricity consumption and of course also our per capita CO2 emissions is also significantly lower than the world. And so this is sort of the numbers, followed by oil. Most of our oil is imported. A lot of the energy that we use is going for electricity generation, and then the electricity is going for industry, residential, commercial. We have a significant amount of biomass which is being used, and then so we can look at that. Now, energy and climate is that we need to see, this is an identity given by a Japanese, actually just rewriting the total CO2 as CO2 per unit energy into energy per unit GDP into GDP per population and to population. And this helps us look at what are the options available for us as a country, as a world, right? We have limited options to control the population. That's not something we are thinking of. GDP per population is a parameter which every country wants to grow. So let's leave these two out of it. Now we are left with two things: energy per unit GDP. That means reduce the energy intensity of the GDP. Two ways of doing this. One is make the products and processes more energy efficient. Second way of doing this, change the structure of the economy so that all the energy intensive steel, cement, etc. is, let China do that, let the developing countries do that. Developed countries have got rid of these dirty industries and their pollution and CO2. We may want to do that or not do that, we have to decide. But also we have to realize there is an implication on employment. Right? So that's the thing. But energy intensity is one. Someone will tell you that you compare with Singapore, and Singapore is so much more efficient than India. But Singapore is more efficient than India because Singapore doesn't make steel, doesn't make aluminium, doesn't make cement. So you have to look at the structure. But energy intensity is one thing. And then CO2 per unit energy, which is the carbon intensity of the energy sector, which we can improve by having more of renewables, more of hydro, more of nuclear. And then of course this is all about sources. We can also increase the sinks. That means we can have afforestation. Then there are many other things we can think of. Okay, let the coal power plants be there, but let's take the carbon dioxide, capture it, sequester it, store it. All possible, but then there are issues. So typically, we have, for the future, based on what we do today, we have three options. You can adapt, there will be some climate change, you adapt. The second is there will be vulnerability, and the third is suffering. So we can mitigate, we can adapt, or we can suffer. These are the three options depending on what we do. Mitigation means we increase the sinks, reduce the sources, and I talk to you about all of this. So just to give you, you can see, you can look at in the world and in India, what are these numbers and how they have been changing. You can see for the world these parameters, how they have changed. And it takes a little bit of time to understand this, what time we can do. In India, if you see, these are the key components. The energy per unit GDP is going down. CO2 per unit GDP now is going down. Per energy, initially it was going up because we had more of centralized fossil. We were moving from traditional. Okay, there are these. What this means is, if we take a base year, let's say we start with 2015 or 2020, and we say, okay, in 2030, if we continue the way we are today, how much would be our CO2 emissions in 2030? And then we want to say, okay, no, we want to reduce that by so much. What are the options available to us? For each option, we can see in the target year how much can we reduce and what would be the cost. And then arrange these options based on lowest cost to highest cost. This is what is done in the global achievement. And this is the McKinsey proposed it. You see a lot of things where the costs are negative. These can be done even without sinking of CO2. They are beneficial in their own way, right? And then you have positive and so this is similar kind of thing is there for India, and you can see this. I'm not going to go into it. So why do we talk about an energy transition? One of the things that we need to understand is that an energy system is not just a technical system, it's a socio-economic system. We have a whole host of, you have the power plants, you have the network, you have this. You can see what happens if for 5 or 6 hours you do not have electricity, how it affects your life, right? So any change in the state of these systems is something which we need to plan for so that we don't have disruptions. And that's why energy transitions are important. I'll skip this. From initially in the 70s, 80s, we had a large amount of hydro, and we had a share, actually the share of renewables was much higher. We have moved to a situation where we are predominantly fossil, and now we are moving back, where we are going back to renewables. This is what we did. We moved in this direction where thermal and nuclear remaining almost constant. Now we have to move back with either going towards much more everything renewables or renewables and also nuclear. In the past, we have moved from traditional fuels to 20-25 years. We've made significant investments in centralized energy supply and distribution infrastructure. We've created centralized interconnected electricity grid, and we've had large hydro and coal-based thermal power plants. The focus has been on supply growth, and most of it has been public sector and government. The next thing is, what is our energy transition? First thing is electricity transition. In the transport sector, we are trying to move away from oil. We are going to CNG, electric, maybe hydrogen, biofuel, methanol, private to public transport, reduce demand for travel and air travel. Cooking energy, we are moving to LPG, but then we have to think of how do we move away from LPG. Is it going to be modern biomass? Is it going to be solar? Is it going to be electricity? Buildings, we can go towards net zero and energy plus buildings, not really happening. Some things there. Industry, we can make our industry low carbon, again not that much happening. Lot of options. Efficiency, renewable, carbon capture, storage, next generation processes. So, what are the drivers for the energy transition? First driver is this climate change and the agreements that we have made, the commitments that all countries have made in Paris and Glasgow, and the prices of shale oil and natural gas. So countries like US, who were once net importers of energy, are now net exporters. It's changed the entire dynamics. We in India have had success in public procurement of LEDs. I'll show you some of this. The other thing which is there is a driver is a rapid development in Internet of Things, and the prices of sensors really becoming low, so that distributed control is now very much possible. One would have liked to think that this would result in distributed energy systems, but that's not happening. Mostly, even with renewables, everything is going centralized, so that's an issue to be followed. Okay, just to show you the success we've had in PV. When we started our solar mission, prices of electricity from PV was about 12 rupees. Now it's like 2 rupees, and you are in Rajasthan, you know many of the projects which are there. So all of this has happened through this reverse bidding, through policy support, and this is something which is it's a dramatic state. Similar thing for LED. LED lights 1,200. Basically through the PSL, what the government did is we created a mechanism where we said we will purchase for Pondicherry, we will purchase for this state, we will do millions of LED lamps, and we gave the purchase, and then we put a tender, and then people came up with lower and lower prices, and then this affected the market. So we've gone down from this to this, and even the market prices have gone. Okay, you can look at the INDC. This was the Paris contribution that we had. We made a commitment reducing the emission intensity of the GDP by 1/3 of the 2005 level in 2030. Create 40% cumulative non-fossil power by installed capacity, additional carbon sink. We are well on target to get there. You can look at, there's a website called Carbon Tracker which tracks every country, and if you see India is green between going forward. Prime Minister Modi in Glasgow has made the following additional commitments, where we are talking of 500 gigawatt of non-fossil by 2030. 50% would be based on renewables, reduction of 1 billion tons of CO2, and by 2030, from 1/3 we said we'll reduce it to by 45%. So that's a much stronger target. And then the interesting thing is we have now committed to achieving net zero carbon dioxide emissions by 2070. And I'll talk a little bit about this. So you can see this is a share of renewables without considering hydro, and you can see share by installed capacity going to almost 25 plus%. You can add another 11% for hydro, then you'll see by it's like 36, 40. So that 40% by capacity is going to be easy. By generation also now it's more than 10%. But in the case of nuclear you can see. So this is the growth. Now what is net zero? There are many different definitions of net zero. And the question is, how do we compute? Are we computing only the direct? Are we computing the direct emissions? Are we computing only CO2, or we are computing all greenhouse gases? Are we computing only annual, or we are computing over the lifetime of the CO2? Accordingly, the calculations are different. Okay? And net zero considering all GHGs at the economy, net zero considering all GHGs at the economy and imports and exports, and net zero considering cumulative emissions. So mostly it is usually this, but you need to see what is the definition when you do that calculation. Okay? And let me explain to you something which we did. We were helping NITI Aayog in sort of looking at this before the target of 2070 was announced. So this is the historic CO2 emission target, a historic CO2 emission trajectory of our country. We had this data and we said, okay, if you project it, this is what will happen. But then we said, because in the last few years we've made several measures, the actual growth rate would be like this. And then we said, now we have two possibilities, where it is we can decide the year in which all NITI Aayog project when we see different years, and then we decided on having 2070 as the target, and the calculation in that was that during this peak year, the GHG emissions per capita would be actually lower than what China was during its peak year. It was also looking at the total, we were looking at the GDP per capita. So there were a number of different, so basically we created a way in which we could have different scenarios of these graphs with different years, and that could help in making the basis. Now, how to go here? There are many different ways, and then there will be changes with this, with the exact technology also changes, but we have to see what can that transition be. What are the issues related to this energy system? Well, you know, the nature of the energy system completely changes when it's predominantly going to be based on renewables. The variability, need for storage, supply-demand matching. Also, there is a climate change impact which shows that if you look at a future requirement, we call it the duck curve. We created it in a lump model where we could create, essentially what happens is as the solar kicks in, the rest of the system needs, after you subtract from the demand the solar and the wind, the remaining portion is what the fossil needs to meet. So you will see that during the time when the solar kicks in, it has to ramp down, and when the solar kicks out, it has to ramp up. And we have to see whether that capability is possible or not. Also, what happens is we made this thing where we can aggregate this. Beyond the point, when you go for higher and higher renewable penetration, at a particular point, any additional solar PV that you get into the grid, that energy is not used at that time, because your demand cannot take anything more. So you have to store it and use it in the evening or the night. And that means that any additional thing, the value of the energy supplied by PV is lower, because you have to add that cost of storage of 5 rupees. And this is, the DISCOMs are understanding this, and then this is one of the issues. The other issue which we thought that we would ramp up our capacity and we would compete. But because of the nature of the bidding, it was typically Chinese companies which got a large proportion of the market. And today we are a net importer. And of course we are trying to correct this with performance linked, production linked incentives and things like that, but it's a challenge because we have to be competitive, we have to compete at those prices of 2 rupees, and this is. Another thing which you need to see is that, you know, all our thermal plants are in Chhattisgarh, Orissa, in the east and central. Most of the renewables are in Rajasthan, Gujarat, Tamil Nadu. So, on a net basis, we are creating jobs, but jobs are being created in a place, jobs are being lost in another place. So, there are regional risks. There are towns and cities and regions which depend on coal. So what will happen? What will be the transition? What are those need to be thought of? So we created a framework where we said, okay, let's take a megawatt and then we said how many jobs of which type and where are the net jobs and things like that. So we need to look at transitions and things like this. So just to give you some idea of our physical progress, this is last year's numbers. You see that already in terms of PV, we are already in the total electricity quite a significant proportion of this. We've also had many schemes for agriculture. Okay, now quickly, I have to also talk a little bit about IIT. So I should give you quick glimpses of what we are doing. We have a number of things going on in energy research. Some portable solar PV towers so that you have some low scale concentration. We have, and I think many of I think we have researchers here, you have a facility for fabrication. We have slightly larger scale heterojunction solar cells which we can fabricate, and I think we have a PE CVD system. I know you have also film and CVD facility. We are working on parabolic trough collectors, direct steam generation. We are also working on thermal energy storage. I also know that NIT has worked in this direction. We are looking at both modeling and experimentation on these and on PVT systems. We have a lot of work on batteries. So whether it's lithium ion, whether it's sodium sulfur, some of these are also where there are prototypes, there are pouch cells, there are we are trying to license, there are some startups, and we have facilities where we can test the cells, we can test the entire packs, and we also doing modeling of this. We have some work already with the renewable power. We have a center of excellence, we have a pilot line for sodium sulfur, and we are planning to do scaling of that. The vanadium redox flow battery, we have an interesting kind of product. Again, some patents there, as well as some licensing, and there's a startup company, this is Kexel. And we also have actually a lot of work on, so this is on air conditioning, passive cooling, thermal energy storage. You have a lot of expertise in these domains also. In the power systems, we have work on each of these aspects, and we are also looking at improving reliability and modeling. Microgrid, number of groups in electrical, in energy, number of groups on microgrid. There are a number of test microgrids, all of the order of 10, 20 kilowatt, and emulators as well as system connected systems. We worked on demand side management and controls, demand response, and I know some of you are interested in this. We've been working on the 5G and then 5G with smart retrofits and controls, smart metering. EV, we have a master's program in electric mobility. I think one of the few in the country which has that. We have the ability to test cells, batteries, the entire EV full vehicle, as well as charging infrastructure. So we have a very nice EV lab, and those of you who are interested, please come and visit. And we have aspects on that. Power electronics related to electric vehicles, smart charging stations. We have an interesting CBG, compressed biogas facility, It's been licensed to two companies, and it's also we have it on campus, and at least one vehicle I know which runs on the campus of the CBD, which is waste. We have some work on biomass heating systems, some work on rural industries, wind and furnaces, pottery, furnaces, furnaces. We have a group working on plasma, and there's a plasma demonstrator for waste. This is an interesting thing. We are looking at coal to methanol along with Thermax, and that's a plant which has been there. The idea is to look at it with hydrogen and CCS. That's the next step. It's a full chemical process plant. It's in Pune, but it's DSD, IIT Delhi, and Thermax. There's a model that we've done some demonstrators, three-wheelers, dimethyl ethyl, DME, basically DME flexible. IOC, the Ashok Leyland, and IIT Delhi funded by DSD. That's the DSD secretary planning it on. Sulfur iodine, thermochemical cycles for hydrogen fuel generator. There's some glimpses just to tell you, show you some of the things. Air quality is an important issue for us. There are a number of things we are doing on air quality. I talked to you about the impact of aerosol and other things on the solar, forecasting, better improved forecasting for wind and power generation, and then the impacts on the policy impacts again from the school of public policy. Okay, this is implications of the hydrogen mission and the rest. So we are like we just heard a presentation from Professor Rohit about the from one of your faculty colleagues of the net zero for MNIT. We are also planning net zero, looking at data acquisition, monitoring, benchmarking, creating a pathway to net zero. We have the following things already. We have 2.7 megawatt peak for solar, and then we are planning some more things. This is sort of the methods that we have. Okay, so I'll close here by saying that we have possibilities of a low carbon future, but this transition has implications. There are challenges and opportunities. There are many costs and impacts. We have to also look at the national priorities, and there is a significant uncertainty, scope for research in technology, systems and policies. We are looking at the campus as a demonstrator. We also want to see how we can provide a competitive advantage for Indian industry, and then look at new technology innovation, and we are looking at curriculum. So I will stop here. I took a little more time than I wanted to, but we'll spend another 10 to 15 minutes for
mentioned Bhutan, who have a carbon negative country.
Yes.
But there are allegations that it is not an economical development happening there. So what is the break-even point that we have to reforestation and at the same time economic development? Thank you, sir.
So I think two parts of your question. And with Nepal, and with certain things where we are looking at Bangladesh and others, there is a possibility of having cross-border trade. And earlier there was talk of a natural gas pipeline coming in from, that would be a pipeline of peace. So I think without very clearly, wherever there are neighbors, where there is a synergy, we are trying to work with them. We have a lot of capability. ONGC, so for some of them, national hydropower, we are looking at investing and also getting the the history of the world is being about control of resources. So you will see also Sri Lanka, Pakistan, all having now currently economic problems. Many of them are, you can see the energy prices are going up. So energy security is very key for us. To the extent possible with some of our neighbors, we will partner. I don't foresee in the immediate future that with Pakistan that is likely to happen. But having said that, there are, they see Bhutan, we're seeing Nepal and many of the others that Yes.
The one small question.
Yeah.
This might be, but we are silent on that.
Not silent on that. What happens is, if you look at the overall global thing, initially our idea was that we said we are only contributing a small part of the problem, and they are not willing to give resources. So in the initial transition, there was a pressure on everyone, every country to declare a year contingency. Right? And most of the countries said that we must do it by 2050. There was, IEA did something that we want to do this by 2050. We said we needed some more time. So we have set, our Prime Minister and our government has set a target that yes, we will go to net zero. But we have almost 50 years and we can do the transition. Silent about net zero, see there are many different pathways. And in the short run, suppose we decide tomorrow we are going to close down all our coal-based power plants, right? We have already made the investment. Who has made the investments? It's typically public sector banks. Someone has to pay for it. The cost of electricity supply. So, what we need to understand is there are costs associated with the transition. We bought ourselves that technology, our economy also develops, and we have employment. I'm not sure whether that answers your question. That's the best answer.
My question was much smaller, sir.
Yeah.
We say net zero future, but we don't say what that net zero is.
Yeah, because actually we don't know. I mean, there are multiple, and whether it will be batteries or green hydrogen, I don't think we should lock into one of them. Right? We will plan for the next 10-15 years. We are saying we will go to net zero. We have a whole host of things we need to look at. So I think that is the reason we do this. Yeah. Yes. Well, I think large population can be seen in a variety of ways. We have a demographic, employment and opportunities. It could be an opportunity. There will be a requirement for energy, so there is a market. If you are not able to get it right, it can be a hindrance. So I'm not quite answering your question in a binary of yes or no. But the point is, we need to understand that there is a development goal and then there is a climate and a sustainability goal. There are some strategies where both may coincide. There are some strategies where there are trade-offs. We need to think that out. Because very clearly, certain regions will get affected. Certain vulnerable populations will get affected. And the whole issue is, we've seen this in COVID also. The economic impact of COVID was felt differently in different economic classes. There are vulnerable populations who will be affected if they have loss of income. So we need to think that out. We need to also, it's not just the end goal, but we need to also think of implementation. Anyone else? Any other? Okay. We're ready. You've already asked a question, so go ahead.
Sir, my question was afforestation and the break-even point.
There is a competing, land is a constraint, right? And on wastelands you can do certain things. So the natural thing is, as population is growing, we are sort of destroying forests. And we can do afforestation, but that needs some will. So we have to work that out. Now, I don't know whether yours is done and others. If it is talking of India itself, the point is that you will see that agriculture, the land, essentially if you see any region, you look at Jaipur itself, what you saw 10 years back for it. There are many other solutions which are being talked of, even with PV. We are looking at agro and PV. So you have crops, or you have plantations and you have PV. So we need solutions like that. Afforestation is where do we use? What are the resources for creating that? Does it affect the rest of our ability to?
Sir, there are techniques like Miyawaki forest. We at MNIT also have it. So is this type of technique useful?
Yeah, techniques, I mean many, see there are whole host of options available. And we have to assess, it's going to be a competition. Yes.
So from years we are talking about depletion of fossil fuel.
Yes.
Yes. No restriction is there. Why?
So actually, if you see now today in the world, the total investments in non-fossil annually is more than the investment in fossil. So very clearly, though fossil is growing, that rate of growth is slowing down. Right? Fossil fuels have been a very convenient way of quickly getting growth and usefulness. So it served its purpose, but we've had a limit. So it's not going to go away immediately. But the trends are there. The writing is there on the wall. That it is declining. It's going to decline. Yes.
So, as a technocrat, we see that we have a we are seeing this problem through a lens of an technocrat.
Okay.
Like how we see the energy to be used, how we are channelizing it. But since it has a social element to it, we should is it feasible to see the people's lifestyle as a to change their lifestyle to sensitize that?
So as I told you, the reason we are studying the transition is because these systems are socio-economic systems. So it is not, in a sense, for instance, large hydro is a very good solution. Nuclear is a very good solution. But when you look at it in terms of people and the perception and the willingness and the areas, that's not socially acceptable. So we need to study. It's not just the technocrat who is going to decide. It's going to affect people's lifestyles. We need to have studies which look at economic impacts. We need to look at sociological impacts. We need to look at impacts on vulnerable populations. And that is what will affect finally the equilibrium. It is not something which is cut and dry. So you are absolutely right. It's not just a technical part. And the transition is not going to be easy. We can make a target, but there are issues in it. There are trade-offs involved. We need to understand that. As technocrats also we need to understand these trade-offs.
I think now the queries are satisfied. Thank you, Professor. The audience are greatly benefited by the insights on the topic. Now I request our director sir to please present a memento to Professor Rangan Banerjee. Being grateful to all those who had contributed toward, I am privileged to present a vote of thanks to all of those who have been involved directly or indirectly in making this lecture a success. Specifically, I would like to thank Professor Rangan Banerjee for sparing valuable time from his busy schedule for such a wonderful lecture. We are thankful to Professor Padi for providing moral, administrative and financial support. My sincere thanks are due to the faculty and students for being here and for patient listening. I am thankful to Professor M.L. Vittal, who is the coordinator for Institute Lecture Series, and Dr. Amar Patnaik for coordinating this event. It is difficult to organize events without the support of the student volunteers, and this lecture is no exception to that. To name a few, I am thankful to Jitesh Sharma, Himanshu Meena and Rupa Singh who have worked hard to make this event a success. Thank you all again. Jai Hind.